Hey guys, one more chance. Quick review. Okay, so the two types of questions you'll get typically is going to be estimating a derivative or estimating an integral. Okay, so if I estimate a derivative, let's say I ask for f prime of 4. Okay, that means you're going to use the 2 points surrounding the 4, this one and this one. Okay, and it's just your algebra 1 slope, change in y over change in x. And yes, I'm in an airport and it's 7 o'clock in the morning. Anyway, so if I ask for the derivative at a point, you use the 2 points surrounding it and do your algebra 1 slope. Okay, now let's say they want units, or they want you to say what it means. Okay, well, we just did change in y. Okay, we did the y's over the x's. So your units are just y's over x's too. So let's say this was given to be hours and this was given to be people, then my units for this would just be people per hour. Okay, pay attention to those units. It helps you figure things out. Now let's change it. Now let's say the f of x was already defined to be a rate and they already called it people per hour. Now what would the derivative represent? It's still y over x, so it'd still be this over this. So it would be people per hour, or people per hour squared. Okay? Sometimes just knowing the units helps you figure out what they're asking for and gives you a free point. Okay, now let's say they ask you to integrate. Okay, if they ask you to integrate on a table, then you're estimating an integral using a Riemann sum or a trapezoid rule or a midpoint rule. Okay, and I'm not going to go over how to do those in this video because we've done that. I'm going to go over how to justify whether that estimate is an overestimate or an underestimate. Okay, so let's say you're asked to do a left Riemann sum for this one. Okay, well, hopefully you know how to do that. That would be 3 times 1, 4 times 1, 6 times 1, and 10 times 1. That would be my left Riemann sum, whatever you get. Okay, now how do you justify whether that estimated integral is an overestimate or an underestimate of the actual integral?
Okay, go ahead.
Okay, to justify a left or right Riemann sum, it has to do with whether or not these numbers are increasing or decreasing. Okay, so quickly look at them. They're getting bigger. So quickly draw an uphill curve, increasing. And it doesn't matter if it's concave up or concave down. You're going to get the same results for a left and right Riemann sum. Then if this is a left Riemann sum, make one big rectangle starting on the left side of your curve, and that has to be the height of the rectangle. Then is this area an over or underestimate of the actual area under that curve? And you can see this is an underestimate. Okay, now the same thing would happen if I used a concave down curve. Starting on the left, make that the height of a rectangle, and you can see that that's an underestimate of the actual area again. So when it comes to left or right Riemann sums, quickly sketch the curve, whether it's increasing or decreasing. Then look at it. Don't memorize all 4 options, just look at it, okay? And you don't have to put that on the paper or anything. They're not going to look at it anyway. All right, so since it was a left Riemann sum, this is an underestimate. And you have to say that it's because f of x is increasing. Okay? That's how you justify a Riemann sum. It has to do with first derivative. You could also say first derivative positive. What you can't say is f prime increasing. That's actually a second derivative. Okay? That would be concave up. All right, so for left and right Riemann sums, just draw a curve and mention whether it's increasing or decreasing. Okay, so just repeating that thought process. If they had done a right Riemann sum, okay, you would still do the same thing. You'd say, okay, oh, these numbers are increasing. I'll quickly draw an increasing curve, and it doesn't matter if it's concave up or concave down. But this time start on the right side and turn that into the height of your rectangle, and you can see that would be an overestimate. Okay? All right, now let's talk about a trapezoid rule. For the trapezoid rule, your justification has to do with the second derivative, concavity. And here's why. Yes, these numbers are still increasing, so I'll just draw a quick curve. That one's concave up. This one's concave down. I'm going to make that into a trapezoid. Use both endpoints, turn that into a trapezoid, and you could see that this one is an overestimate of the area under the curve, versus this one is an underestimate of the area under the curve. So the fact that it was increasing didn't really matter. It's the concavity that matters. So concave up and concave down. So for the trapezoid rule, it has to do with the second derivative, or concavity. Okay, so let me show you how to find that. Okay, first find your first derivatives. Okay, subtract y over x. This one's 1. Subtract y over x. This is 2. Subtract y over x. This is 4. And subtract y over change in x, you'd get 5. Okay, these are my first derivatives. Now look and see if these are getting bigger or smaller. My first derivatives are getting bigger. My first derivatives are increasing, which is the same as second derivative positive. And you can say either of those, okay? Then off to the side, you go, okay, well, that means concave up, and I do a quick, oh, this is an overestimate. Ah, got it. Okay, so just draw it each time. Don't memorize all of the scenarios. Instead, memorize what makes that difference. So let me summarize. So to summarize, if you use a left or right Riemann sum, it's the first derivative that you use as justification, or you say the original function is either increasing or decreasing. For a trapezoid rule, you use the second derivative, okay, or first derivative is increasing or decreasing. And again, that's only if they ask you to justify whether your answer is an over or under estimate.